Welcome to my talk. Before I begin, I'd like to thank the session conveners again for inviting me to give this talk. Today's presentation is titled Assessment of Antarctic Ice Shelf Surface Drainage Structure Using High-Resolution Elevation Data and Cloud Computing, or Water on Ice. Before I begin, I'd like to thank my advisor, Jonathan Kingslake, as well as all the people listed below. Without their help, this work would not be possible. So let me begin by describing what we know already about meltwater systems in Antarctica. Meltwater drainage forms in the summertime and is found to be widespread, existing not just on the relatively warmer Antarctic Peninsula, but all around the continental margin. It's been found to be persistent, occurring not just in anomalously warm years, but multiple times per decade, if not every year, and large scale, carrying water from the grounding line tens of kilometers towards the Kelvin front. And while meltwater is not a major contributor to ice mass loss in Antarctica, it has been connected to a number of effects on the ice shelf system overall. First, the albedo melt positive feedback loop. Meltwater is darker than the surrounding ice and snow, and thus absorbs more solar insolation, which in turn leads to more melting. Also, because liquid water is denser than solid ice, we find that when meltwater ponds, this can actually cause the ice shelf surrounding it to flex. When water enters pre-existing crevasses, the water pressure can propagate these crevasses all the way to the base. In fact, it's been hypothesized that rapid drainage events can even be connected to ice shelf collapse. The collapse of the Larsen B ice shelf in 2005 has been connected to the rapid drainage of hundreds of lakes that occurred beforehand. Even more alarming, recent modeling work by Trutzl et al. Found that Antarctic meltwater volume is expected to double in the coming century. So the focus of my work is the intersection of these three circles in the Venn diagram. First, where is meltwater forming and ponding, and what controls the extent of the meltwater drainage network once it forms? This has been the focus of my previous work. Two, where is the ice shelf susceptible to hydrofracturing, and where is it important for upstream buttressing? Those are the bottom two circles. And currently, my work is focusing on the intersection. What would be required for meltwater drainage to bring water to areas that are susceptible to hydrofracturing? Or what is in the middle of this Venn diagram? We already have previous work, for example, the work of Yao Lai et al. In 2020, that used machine learning to investigate what areas of the Antarctic ice shelves are vulnerable to hydrofracturing. And so we can see in red areas that are expected to have crevasses that are in the correct stresses to allow for hydrofracturing. And we have a lot of really important information from remote observation. So first, we have a wealth of satellite imagery, both optical and synthetic aperture radar, which gives us information about the growth, the depth, the volume, and even phase change. So in my previous work, I used a time series of synthetic aperture radar images to hypothesize the freeze-through of many of these surface lakes during the austral winter. And even more recently, we have some really amazing altimetry results from projects such as ISAT-2, which has been able to measure, possibly for the first time, the flexure around a rapid draining lake. And this is the work of Warner et al. In 2021. But if we want to investigate where water is going to flow in a warmer, wetter future, and how is water going to be transported to these red, vulnerable to hydrofracture areas, we really need to know about where water is going to pond and drain in these areas that don't have a historical record of surface melting. So over in the area covered by the question mark, where is water going to flow? Thankfully, we have some understanding of water flow and routing in general. We know that water is going to flow into topographic depressions, and we can use some present day topography to understand where water might flow once it's overspilled out of the areas that we know it to be. And so there's a relatively recent high resolution Antarctic digital elevation model called REMA, the Reference Elevation Model of Antarctica. It has 8-meter resolution in the horizontal direction, less than 1 meter vertical resolution, and covers 98% of the Antarctic continent. It's amazing. But some complication, it's over 1 terabyte of data, and even one tile is over a gigabyte. So proves to be a little bit difficult to work with on your home computer. Furthermore, while the RIMA dataset has been extensively pre-processed to remove a lot of the artifacts associated with DEMs, there's still a number of satellite artifacts. I found these sub-meter scale deviations in the elevation on the surface of many of the ice shelves. And if you can't see it, it's a little bit more visible in this second derivation. So you can see kind of oblique to grid north, you see a bunch of these lines, but you also see these naturally forming flow stripes. So in order to remove them, we need to make sure to identify which ones are the oblique stripes and which ones are the flow stripes that we want to preserve. So the first step is to use a Franchi filter to identify long ridge-like structures. Then we can use ice velocity data. Here I use measures ice velocity data to get the flow orientation in order to identify these flow-oriented or flow-aligned flow stripes. So then we can identify which are the flow stripes and which are the oblique artifacts. So in this case, the oblique artifacts have an orientation of about 1 radian compared to 1.5 radians for the flow stripes. Then we can use this oblique stripe removing algorithm, which is a super Gaussian filter developed by Voigt et al. In order to remove these stripes from the DEM. And here we have it, a processed DEM ready for catchment delineation. But this is only one piece. And while it's really exciting that this process is relatively straightforward, if we were to try to do this by hand on a home computer, we would find ourselves doing the same thing thousands and thousands of times. This is where cloud computing really is important. I've been able to use a cloud platform called Pangeo in order to both store these large data sets in the DEM in these storage nodes, as well as use the parallelizability of Dask and cluster computing in order to do this pre-processing step across tens of gigabytes of data, all while using just a home web browser on my laptop. If you're interested, I highly recommend visiting gallery.pangeo.io to see a gallery of amazing examples of how Pangeo can be used. So now that we have our pre-processed DEM, we can use a simple 8-directional catchment delineation model or algorithm in order to identify which areas of the surface drain into each surface depression. And we can do this on multiple levels, either choosing to connect upstream and downstream, or just have no connection at all. And here is a little rotating GIF of what these DEMs look like and what the catchment delineations look like. So in red and yellow are 2 examples of a catchment, 2 catchments. So I've been practicing these algorithms on 5 ice shelves with histories of surface melt observations: the Larsen C, the Reiser Larsen, Nibelsen, Rabajuan, and Amory ice shelf. So here we have the raw or disconnected catchment system. So each of these tiny catchments is just one single basin. When we agglomerate the basins a little bit to include kind of larger scale basins that contain these smaller basins, we can see the agglomeration of some larger catchments by the grounding line shown in black, as well as many tiny catchments in the kind of areas in between. We can even go one step further and connect upstream to downstream areas to create what is effectively terrestrial riverine catchments. So you can see these large catchments that connect the grounding lines to the ocean or calving front shown in black. But I should warn you that if you want to do flow routing, you're going to need to fill in these areas of missing data, which create these artificial separations in the catchments. And so the focus of this initial kind of proof of concept is to investigate what topographic conditions are associated with rapid downslope extension of surface drainage networks during an austral summer. In other words, how do we get water from areas with observations of melt into those question mark areas where we do not? So we do this by first investigating the properties, the hydrological properties of each of these catchments. We can look at the percent coverage by lakes, shown in A. You can see that areas that are most covered by lakes are also seem to be by the grounding line. B, catchment area. Again, we see the largest catchments by the grounding line. Basin volume. Again, we see the most voluminous catchments by the grounding line, and maximum depression depth. So the deepest point in the basin, those deepest areas are found in, again, catchments by the grounding line. And this pattern exists not just on Rob-a-Dwan, which is the example here, but on all of the catchments that we investigated. We see kind of a pattern in each case of kind of large, deep, and kind of difficult to fill catchments around grounding lines and downstream of exposed rock or nunatex. So here I'm using the ratio of basin volume to catchment area, which we call R, as a metric of the susceptibility of a catchment to overspill to overtopping. In red, we see catchments that are quote unquote easy to fill with low volumes and high catchment areas. And in blue, catchments that are quote more difficult to fill, so high volumes and smaller catchment areas. Because catchment melt input is related to the surface area available for melting, we can kind of compare these two as sort of the metric of how many meters of melt per unit area are required to fill up the basin in each catchment. So the next step is to compare the kind of unitless or timeless, I guess, melt metric, this R, to the output of a regional climate model. So here we're using the regional climate model RACMO, which is a gridded climate reanalysis model run over 1989 to 2018. And one of the daily outputs is annual melt. And we can then take the mean annual melt and compare it to these catchments. So these are two-dimensional histograms. On the y-axis is log 10 of R, that ratio of volume to area. And on the x-axis is the average annual surface melt from RACMO. Everywhere below the red line is able to be filled by RACMO melt in a single year. And we can see that there are many catchments that are able to fill, but there's also populations of catchments above the red line that are not able to be filled in a single year. And we can see this spatially in these plots here. So again, in blue are catchments that are unfilled by the annual average RACMO melt output. And in yellow and red are catchments that do. And again, we see the same spatial pattern. Areas of blue are clustered by the grounding line, and areas of yellow and red are immediately downstream. And kind of a peek into future work, we're interested in how future melt is going to fill these catchments. So we did a very similar comparison between our catchments ratios, R, and the outputs of a number of Earth system models that are modeling melt output from RCP 8.5. And you can see all the catchments that are not black are filled to overfilling. And so the point of all this is to try to investigate where we expect melt to overspill in the next century and arrive over areas that are vulnerable to hydrofracture. So the kind of takeaway points from my presentation, areas that are most susceptible to rapid downslope drainage networks are large shallow catchments. And while these areas may not have been observed to be filled by meltwater in the satellite imagery record yet, we have evidence that they are downslope of catchments that are expected to fill in the next century. So it seems fairly obvious that once you overspill these deeper catchments, that they'll be able to flow across these shallow areas. But by using these various methods, we can show that this is a process that's going to happen on at least 5 ice shelves that have a history of melt. And this all comes back to the intersection of this Venn diagram. Where is there going to be water? Where is susceptible to fracturing? And where is important for buttressing? I'd like to thank you again for listening to my talk, and please feel free to send me any questions you have about my work. Bye.